Welcome back. Okay, morphine, morphine the prototype, and a variety of other opioid agonists as well. You put something into the body, it's going to have some type of activity, but the body's response is to process that molecule and get it out. That's the purpose of a lot of enzymes and organs in our body. And it turns out that when we talk about morphine metabolism, morphine can undergo both phase one and phase two reactions. Remember, phase one reactions are oxidative, and phase two reactions are conjugation reactions. And oxidative reactions typically allow for conjugation to occur. But if there's already a handle on your drug molecule, you don't need oxidation. You can go right to conjugation. And that's kind of what happens with morphine. Now, think back to the structure of morphine. Do we have a handle already in place on morphine? And the answer, of course, is yes. So we have an alcohol at the 3 position. We have an alcohol at the 6 position. So those theoretically are handles right there. All right. Then what else can happen to morphine? And that's where this phase one is going to come in. But where? Where is it going to happen? And it's going to happen on the top side where the methyl group is going to undergo N dealkylation. All right. Now this 3 position, glucuronidation. Morphine 3 glucuronide. Same thing at the 6 position to arrive at morphine 6 glucuronide. And then N-dealkylation catalyzed by CYP3A4, you're going to end up with normorphine, right? So you have 3 different metabolites that can be synthesized by your body after this molecule has passed through, say, the liver. Okay. Of those 3, are any of them active? Well, normorphine, plops off the alkyl group, the methyl group, right? And then you generate a secondary amine from the tertiary amine. And despite the fact that normorphine can still be ionized, this lacks activity. And the morphine 3 glucuronide, remember that hydroxyl group at the 3 position is critically important for binding and intrinsic activity. But when you stick glucuronic acid at that 3 spot, you lose activity because you lose that H binding interaction. Morphine 6 glucuronide is actually active. And remember, the ligand binding domain of the opioid receptors has got quite a bit of real estate. And when you stick glucuronic acid at the 6 position on morphine, that creates then additional binding interactions whereby morphine can interact with the receptor despite the presence of that glucuronic acid, right? So morphine 6 glucuronide. Other opioids, something to consider. Here's a question for you guys. What must occur, right, to these particular molecules before they have activity? Well, let's survey them really quick. Look at the north side, top side. They all have that tertiary amine ionized, so that can afford us with ionic interactions. Alcohol at the sixth position, carbonyl group at the sixth position, carbonyl group at the sixth position. All right, so H bonds can happen. What's here at the three position, though? These are all blocked because these are methyl ethers, right? Or methoxy groups. Okay. Remember, at the three position, you need that alcohol, right, to bind. But there is a caveat here. This molecule, we'll come back to that in a second. This is codeine. This is hydrocodone, and this is oxycodone. Codeine, as it gets processed by CYP2D6, that enzyme will remove that methyl group, and you'll end up generating morphine. So you can argue that codeine is a prodrug leading to the formation of morphine after it gets metabolized by CYP2D6. Hydrocodone, after it gets metabolized by CYP2D6, generates hydromorphone. 2D6 will remove that methyl group from hydrocodone to make hydromorphone. And then oxycodone. Well, guys, the presence of that alcohol at the 14 position makes oxycodone active. It's active right now as is. It doesn't need to get O-dealkylated for activity. So oxycodone, as the parent molecule, retains potent opioid analgesic effects. But I can tell you that as oxycodone proceeds through 2D6, and 2D6 dealkylates that alcohol, you end up forming something called oxymorphone or opana, which was a pretty potent opioid analgesic as well. I don't think it's used very often anymore, though, today. All right. So know the difference then in terms of processing, which ones kind of need to be processed in order to display potent opioid analgesic effects. All right. And then before we take a break, here's a survey of the structures. Again, the prototype is morphine. Codeine is the methyl ether analog of morphine. Codeine gets converted to morphine via 2D6. Hydrocodone is the methyl ether analog of hydromorphone. And again, 2D6 will convert hydrocodone into hydromorphone, but oxycodone stands alone because of the alcohol at the 14 position. It is active as is. Okay? All right. When we come back, we'll talk about additional opioid agonists. See you in a little while.